Hey, so these are the physics notes for 11.1 through 11.6, where we're starting to talk about the basics of what we call SHM. I'm trying to say words and spell at the same time. Simple harmonic motion. And this is something that's periodic in behavior, and that can be represented by a traditional sine wave. You think about the concept that something is oscillating over and over again. A couple of really simple examples that we use in physics all the time would be a mass on the end of a spring. Okay. Now every spring is going to have a stiffness constant. We'll call that K, and it's measured in newtons per meter. Okay, so it's newtons per meter. Depending on how stiff the spring is, you're going to have a bigger K or a smaller K. So this is our mass down here. Now the idea is that when this mass is pulled down, that it's going to end up vibrating up and down. You're going to see it oscillate from the center up to a certain height and down to a certain height. And that it's going to do this on a cycle over and over again. Now if you can imagine watching that happen as it slides to the right, you would see it creating a sine wave. And that's exactly what we mean by sinusoidal or periodic behavior. It'll repeat itself. Now what's really cool about it is that the time that it takes to complete one cycle is constant and is based only on the mass and the stiffness constant. Those are the two values that are going to derive or determine how long it takes for this oscillation to complete itself over and over again. So this becomes a way for us to maintain or keep track of time. We can also make predictions about how fast it'll be moving at different points, things along those lines. To be able to work with springs, we need a couple of different things. First, we need a formula that defines what K is and how do we measure it. Now, the traditional formula that we used earlier in the year is that the force that a spring applies back on something, on a mass, is equal to negative K times any displacement change. So you can imagine the spring is sitting there holding itself still. Well, that means that the spring is pulling up with a force that is equal to the weight down. If we find that equilibrium point. Now any extra force we do, that's beyond that. But when it just sits there, it's stretched the spring. Well, the spring is pulling up with the same amount as the weight of the object. And so we can determine a lot about the stiffness constant. Now the problem is that this delta x is a change in length. If we do not know the original length, this formula doesn't quite work for a lot of the problems you're going to see. Quite often, you're going to look at, hey, I added some mass, and we saw a specific change. So don't be surprised for the formula to actually come out as a change in force equals K times a change in X. The way that would look traditionally would be, hey, we went from 20 newtons of weight on this, we added 5 more newtons, so that would make it, you might think it's 25 newtons, but really it's a 5 newton change, and we notice it stretched 2 centimeters, so our delta x would be 0.02. So those are the kinds of things where maybe we're looking more at a change of 5 newtons equals K times 0.02 meters, okay, and that would allow us to find the K for that spring that I was just talking about. Where people sometimes get into trouble is they assume that this needs to be 25 because that's the mass or the weight of the spring, but this is the change not from 25 but just from 5. So you have to really think about, you know, what amount of force or what weight causes what stretch. So that's just something to be thoughtful of when you use this formula. And you'll also notice that I dropped that negative off. I did that on purpose. I know that the force the spring applies is going to oppose the stretch from the spring. And so that negative just tells me directionality, it's backwards. That if I'm pulling down with a weight, the spring is obviously pulling up. If I'm pulling to the side to the right against the spring is pulling to the left. That negative doesn't actually connotate a value there. We would have to acknowledge that the F in this problem would be a negative, and so that would cause the negative to cancel anyway. So generally speaking, it's not something that you computationally need to worry about. It's just a matter of the application is backwards. The other thing that you're going to need to understand, there are times when we press a spring together or we stretch a spring and we know there's some energy that's been stored in that spring. So if we need the potential energy that's stored in a spring, usually this happens when we're talking about, hey, when I let go of the spring, how fast is something moving? That would be a conversion from potential to kinetic. So we kind of need to know how much energy gets stored in a spring. And that formula is 1/2 K, the stiffness constant, times the displacement squared. How much stretch was there? You know, if you look at this spring and it was stretched 0.02 meters, well, that would be my delta, that'd be my x, and I got to square that. The reason we would use this is, again, let's say I take a spring and I squished it down. Okay, so I'm going to make it delta x here. I'm going to squish it down. When I let go of the spring, it's going to shoot upward, and it's going to give some velocity to whatever's on top of it. So if I put a ball on top of that, it's going to shoot the ball upward and give it kinetic energy. So you might see something where this transfers to kinetic energy, which we know is 1/2 mv squared. So there's things like that. We could figure that out. That, hey, this kinetic energy is coming from the spring, and the spring is stored that amount of energy. All right. So there's kind of your spring values when you talk about how do you use K to help with stuff. Well, now we have to talk about actually working on finding this time that it takes for a cycle to be completed. With springs, okay, so all of this stuff has been spring related. The time for a spring oscillation to be one cycle, okay, to complete one up and down movement all the way through, is equal to 2 pi times the square root of the mass of the object on the end divided by the stiffness constant. Now that's all inside the square root. It's really important you keep track of that. The reason that these other formulas come up so often is because they're actually really good ways of trying to determine what K is. If I can figure out how fast a ball is shot off the end of a spring, I can actually use that to determine the stiffness constant of the spring. And so this right up here often comes down to finding K first. And so we might have to dig K out of one of these other formulas. And that's why that information is brought up here. All right? The other thing that we talk about all the time is a pendulum. Okay? And a pendulum, we know, swings back and forth. Back and forth. It's going to hypnotize you. As it swings back and forth, it also has a cycle. If we call this t equals 0, it's going to go all the way down and all the way back. And if we looked at its position over time, it also follows a sinusoidal pattern, meaning it does, okay, starts at 0, okay, goes up, hits a 0. So if you think about this in terms of like its velocity, it's really slow, it gets fast, slows down, speeds back up, but going backwards now, so negative, and then comes back to a resting point. That's what we're seeing with the pendulum in its sinusoidal behavior. And the period, or the time it takes for a pendulum to complete its cycle, is equal to 2 pi times the square root of the length of the pendulum divided by gravity. Again, all of that's in the square root. There's our length. How long is the pendulum? And then, of course, gravity. Now, when we talk about simple harmonic motion, and we talk about the stuff that we're going to continue to talk about, waves and wave behavior for the rest of the semester, we really don't talk about the period or the time it takes near so much as we talk about the frequency of something. Whether that's the frequency of a sound or a light wave or some other type of electromagnetic wave, we're constantly looking at frequency, and eventually we talk about something called wavelength. We won't deal with that in this section, but this idea of frequency. So no matter how we're finding the period, whether it's a spring or a pendulum or some other type of wave or sinusoidal behavior, the frequency, which means a script f like that, is always equal to 1 over the period, 1 over the time it takes to complete a cycle. So the way this looks when we're all said and done, okay, because remember, time is measured in seconds. We end up with a weird unit, a 1 over seconds unit, because that just is weird. And so over time we decided that frequency needed a unit, and so we named it after someone who had a lot of work with the idea of waves and wave behavior. And we say that frequency is measured in hertz. We use a capital H and a little z. So let's say that your period for something is 1/2 a second. It completes a cycle in 1/2 a second. So if t equals 0.5 seconds, then the frequency is 1/0.5, and that comes out to be 2 hertz. Okay? So when you hear numbers that are large number of hertz, like megahertz or gigahertz, these things mean that the cycle is being completed very fast, like microseconds. Its cycle has to be so fast. I mean, if you complete in 1/2 a second, you get 2 hertz. If you complete it in 1 second, you get 1 hertz. So this has got to be really small to get large number of hertz. So when we talk about frequencies, we're talking about things that are repeating that cycle very rapidly. Essentially what we're asking is, how many cycles get completed every second? That's what a frequency is. How many times does it complete the cycle in 1 second? I'm hoping that there's enough here to help you. When it comes to the pendulum, I will kind of warn you of one thing. One of the really common classical questions is based around a little bit of trigonometry, and that is, asking how fast is it moving at the bottom. If we look at this as a transfer of energy from potential energy at the beginning to kinetic energy at the bottom when it's at its low point, this height difference here is the key to finding the whole thing, which means you need things like the length and an angle to be able to find this side here. We'll call that x, and using that x compared to the length, you know that there's a shortening. It's shorter than the length by a certain amount. Okay, and that's what we'd be looking for. You're going to commonly have to do that if you're looking at a pendulum and being asked about velocities. That's basically where you're going to have to go with that. All right, I hope that that's enough to help you with the homework for 11.1 through 11.6. We'll see you in class, and good luck.